Good morning, good afternoon, good evening, depending where you're connecting from. My name is Pedro Mendoza. I'm a solutions architect in the AWS IoT team, and today it's my pleasure to present a session on how to set up a private LoRaWAN network using AWS IoT. This is the agenda for today. We will start doing some introductory explanation of the LoRa and LoRaWAN concepts, and then we will move into explaining the benefits of bringing together LoRaWAN and AWS IoT. Next, we will dive a bit deeper into the process to actually set up the gateways and device in order to be able to connect to AWS IoT Core for LoRaWAN, and we will dive deep into the different components that build up the AWS IoT Core for LoRaWAN service. We will also inspect some of the key flows within the service. Finally, we will do a demonstration of a solution that is using the service, and we will finish the session by including some reference to what our customers are already doing using the service. So let's start with the LoRa and LoRaWAN introduction. These are basically the technologies underlying the technology that we are explaining today. LoRa is one of the technologies in the LPWAN family. LPWAN, that stands for Low Power Wide Area Networks, is a set of technologies that are intended for devices that need to send a small amount of data over long distance. In addition to LoRa, there are other technologies in this family. You can find as well Narrowband IoT, LTM, or Sigfox. As I mentioned before, these are technologies that are aimed for devices that are really constrained in terms of usage of power. That's why these devices need to run, for example, over 10 years and are typically battery operated. What makes LoRa special in the family of LPWAN technologies is the fact that it uses unlicensed frequency spectrum. As a consequence, it is possible for the LoRa users to set up their own private networks. LoRa and LoRaWAN are terms that are typically used together, so let's spend a few seconds to explain the difference between them. LoRa is the communication protocol that is used to translate the data captured by the sensors into electromagnetic signals that can send to the gateways. On the other hand, LoRaWAN is the set of open standards that are used to interconnect these devices to form larger networks. LoRaWAN technologies are basically managed by the LoRa Alliance that includes over 500 members, and AWS is one of these. Let's take a deeper look into the different components in the typical LoRaWAN network. From left to right, you can see the LoRa devices. These are sensors or actuators that will be actually capturing the physical signals and sending it over using the LoRa protocol. This message will be received by the LoRa gateways that will basically be devices that are connected using cellular connectivity or Wi-Fi or Ethernet, and will be basically forwarding this message coming from the devices into the LoRaWAN network servers. There are two main packet forwarder technologies, the legacy packet forwarder, which is using UDP protocol, and the newer basic station that uses TCP and specifically secure WebSockets to send the data to the LoRaWAN network servers. The next component in the diagram, the LNS or LoRaWAN network server, is the component responsible for actually receiving that data from the gateways and sending it to the consuming applications. In addition to that, the LNS is also responsible for deduplicating the data. As you can see in the diagram, the same device can reach the LNS using different or more than one gateway, so that's why it's important that the LNS perform this data deduplication. It will also be responsible for ensuring the authenticity of the devices connecting, as well as the integrity of the data. Complementing the LoRaWAN network server, we have the joint server, who is a component responsible for generating the security keys that are going to be used to ensure the confidentiality of the communication. We are using in LoRaWAN technologies two different keys. The first one is the network session key that ensures confidentiality between the device and the LNS. And the second is the application session key that does the same, but in this case, between the device and the application server. These keys make use of the standard advanced encryption standard cryptography. So what is the application server? The application server is where actually the solutions are built based on the data ingestion from the LoRa devices. These solutions can range from simple storage and visualization solutions up to more complex things like, for example, doing machine learning based on the data ingested from the devices. Now let's dive a bit deep. Once we have the concepts around LoRa and LoRaWAN, let's dive a bit deeper into the actual integration between these technologies and AWS IoT Core. Combining the benefits of these low power, long distance characteristics of LoRa and LoRaWAN technologies with the richness of the AWS ecosystem is a very strong value proposition for our customers. That's the reason why we have designed AWS IoT Core for LoRaWAN as a managed service to enable the deployment of private LoRaWAN networks that can easily and securely connect to AWS IoT Core. On top of it, our customers can then leverage the richness of the integration between AWS IoT Core and the rest of the AWS platform. Some of the characteristics of this managed service are its high scalability and security. So by providing these dimensions to the customer, we allow them to actually focus on what makes their problem unique, which is basically generating business value using this technology. I would like to double down on the fact that the customer will not need to worry about any operational concerns that is actually undifferentiated from one problem to another. We will take care of patching the software, underlying the service. We'll take care of dealing with an increase in the traffic coming from devices and all these dimensions. Finally, if we refer to the previous diagram, as you can imagine now, the overall AWS platform is replacing the traditional role of the application server. So let's dive a bit deeper into the process to set up and integrate both gateways and devices into the AWS IoT Core for LoRaWAN service. First, let's talk about the gateways. As we mentioned before, the gateway's responsibility is actually forwarding these packets that are coming from the devices towards the LoRaWAN network server. In the specific case of AWS IoT Core for LoRaWAN, we require that these gateways are running basic station packet forwarder protocol, and it will use TLS 1.2 and specifically mutual authentication to secure the communication channel from the gateway to the LNS. It will implement this mutual authentication based on X509 certificates. In terms of protocols, for the data plane, it will use secure WebSockets and will use HTTPS for the management and configuration connectivity with the COPS component in the LoRaWAN network server. In terms of gateway selection, you can basically choose between two options. First of all, we have been working with the major gateways manufacturers in the industry to qualify a set of gateways, so it's very easy to set this up and integrate with AWS IoT Core for LoRaWAN. These are gateways that are pre-configured with the right endpoints as well as the required certificate for implementing this TLS mutual authentication. So it will be a single configuration step to get this up and running. Alternatively, you can also use off-the-shelf gateways. In that case, you will need to make sure that you are filling all the requirements, and you will also be responsible for configuring the endpoints in order to connect to the AWS IoT Core for LoRaWAN service. You will also need to upload the vendor-provided certificates. At the bottom of the slide, you can find a link with all the devices that are already qualified to properly work with AWS IoT Core for LoRaWAN. This is just a sample command that shows what are the input parameters required to configure a gateway in AWS IoT Core for LoRaWAN. As you can see, it's a really simple command. All you need to provide is the gateway EUI, and in this case, we are referring to one of these pre-configured gateways, so it is also provisioned with the right endpoints and also the required certificate. Moving to the devices, in this case, we are talking about devices that supports either the 1.0.x or 1.1 LoRaWAN specification, right? And we support both over-the-air activation as well as activation by personalization mechanism. The main difference is that in ABP, or activation by personalization, the keys, the security keys that guarantee the confidentiality of the data transmission, are pre-programmed, so it is less flexible. On the other hand, OTAA is using keys that are dynamically generated. These are keys that we will dive a bit deeper, are generated by the joint server and it is the joint server responsibility to actually distribute this to both the LNS as well as the application server. Finally, I would like to mention that, as happens with the gateway, once the device has been registered with AWS IoT Core for LoRaWAN, it will be listed as another thing in the AWS IoT Core thing registry. This is an example for how you can actually run a command that will register a new device in AWS IoT Core for LoRaWAN. In this case, this is a device using OTA, or which basically stands for over-the-air activation, which is the mechanism for generating these keys in a dynamic way. In addition to the device EUI, application key, and application EUI, you can see in this command line that you should also provide a destination, which is basically the name of the rule in AWS IoT Core that will be responsible for processing the message that will be ingested coming from that device. We will dive deeper into the intent of this rule in a second. Now that we understand what is the process to set up the gateways on devices, let's take a deeper look into the different components that are inside the AWS IoT Core for LoRaWAN service. We can see we have three main components. First of all, we have the LNS. As we mentioned, it will be responsible for doing data decryption. It will also be responsible for deduplicating the message in case the device are using or is reaching more than one gateway. It will also take care of validating the authenticity of the device as well as the integrity of the data being transmitted. Last but not least, it is responsible to forwarding the uplink message coming from the device to the downstream consumers, in this case IoT Core, and also doing the opposite one, so being able to send the messages coming from AWS IoT Core down to the devices, what we call the downlink messages. In addition to the LNS, we have two other components in the service. We have the COPS, which is responsible for gateway firmware and configuration tasks, and we also have the joint server that, as we mentioned before, is the one that uses or generates the security keys, both the network session key and the application session key, to ensure the integrity of the communication between the device and the other components in the LoRaWAN technology. Okay, so let's take a quick look at the uplink data flow. As we mentioned, this is the flow that comes from the device up to the AWS IoT Core for LoRaWAN service. First of all, as we mentioned, the device during the configuration phase has been configured with a destination that is where the actual message will be processed. This is part of the AWS IoT Core rules engine, which is basically a component intended to ingest large amounts of data at low cost. The rules engine has capabilities for filtering, transforming, and finally routing this message into final destinations, what we call actions. These actions include storing in DynamoDB or S3, but also integrating with other services like SQS or SNS for alarming or notification use cases, and can also do more complex tasks like, for example, sending messages to AWS IoT Analytics or AWS IoT Events. We will dive a bit deeper as part of the demo. An important characteristic of the integration of the LoRaWAN devices and the rules engines is the fact that due to the bandwidth constraint that is associated with the LoRaWAN devices, they will typically send data in an encoded format. That's why, as you can see in the diagram, the very first step is to decode that payload so it can be properly consumed by the downstream consumers. That's actually the role of the Lambda function that you can see in the diagram. Once decoded, there is a rule that will be republishing that message into another topic, and then it can be consumed, like, for example, by Amazon S3 or Amazon SQS in the example. It could be any other of the actions supported by the rules engine. In addition to the task or the features to ingest the data and also send downlink messages to the devices, AWS IoT Core for LoRaWAN also includes features for monitoring the status of the gateways on devices. Specifically, you can get information about the frequency being used by the device, but also about the data rate, the different gateways that are receiving the signal, and also the signal strengths, other indicators such as the signal to noise ratio. In addition to this management task, The gateway firmware can also be updated using the COPS component, and you can also use, as we have been discussing, the AWS IoT Core for LoRaWAN features for sending message down to the device, what we call the downlink messages. So now let's take a quick look into the demonstration. Before we actually get into the architectural diagram and the console, I would like to show a bit of a context. So the demo today is about monitoring the health of a plant, right? So we'll be basically sensing the level of moisture in the soil where the plant is living, and we will use that information in order to model whether or not the plant is healthy. So let's first introduce our components today. So we have our plant, right? We have our sensor. In this case, it's, as I mentioned, it's a soil moisture sensor, right? We'll be sensing the signal here, and it will be connecting over the LoRa network. And finally, we have our gateway. This is one of these pre-configured gateways that has been already configured to be able to connect to AWS IoT Core for LoRaWAN, correct? This is coming from one of our partners. So let's go first into the architectural diagram. As I mentioned, the intent here is to basically sense the level of moisture in the soil where the plant is living, and we'll be using a LoRaWAN sensor for that. This sensor will be basically sending the data to a gateway that will basically forward that information as the gateway's role into the LoRaWAN network server. In this case, this data is eventually going to be ingested in the AWS IoT Core for LoRaWAN. As you might imagine, both the gateway as well as the device has been already registered with AWS IoT Core for LoRaWAN using commands similar to what we saw before. In order to be able to actually process this message, this device has also been configured in order to target a specific rule in AWS IoT Core rules engine. As we mentioned before, one of the attributes in the message is actually the level of moisture in the soil. And that's exactly what we are doing. Well, as we explained in the previous diagram, one of the first tasks that we need to do once we have ingested the data is actually proceed and decode this payload because of the restrictions associated to the bandwidth of the LoRa devices. We basically need to transform it into something that the downstream consumers can actually use. We do that by invoking a Lambda function that is associated to a rule in IoT Core. Once we have decoded the payload using the Lambda, we can then republish that information into another topic. This topic is also associated with a second rule that will simply forward the decoded payload into a detector model implemented in AWS IoT Events. This is the model where we'll basically identify what is the state of our plant. Finally, whenever this model transition from one state to another, we will see that in a second, we will be sending a notification to the user. We do that by sending an SMS message that is actually coming from an SNS notification topic. In addition to getting this notification over SMS, the user is able to also monitor the status of the plant and actually even inspect the message by using a web application that has a subscription into the MQTT topic that contains the already decoded payloads. In addition to that, there is another data flow that is about sending data down to the device, but I suggest that now we move into the actual console and we see the application in action. We can then later get back to the downlink use case. So this is the web application that the user will basically see. It is composed by two different views. First, we have the business user view, which, as you can see, simply render the level of moisture in the soil, and is complemented by a technical user view, where we are actually dumping the message, both the encoded as well as the decoded version of the message. You can see in the upper section, we had the encoded payload, and then in the bottom of the page, we can see the already decoded attributes, including the level of moisture. Complementing that, you can see that we also have some metadata information included in the message. As I was referring before, you can see there which gateways has received the message, and you can also see other indicators like, for example, the frequency or the signal-to-noise ratio. As you can see now, we are really getting a 0 reading from the sensor, and the reason is because the sensor is just not inserted into the soil. Let's take a look into the actual message by using the MQTT client that is part of AWS IoT Core, and we can see here both the encoded as well as the decoded payloads. Now let's follow the trail of the data. So the first thing we do is basically we have a rule that, as we explained before, will be associated to the topic where the data is still encoded, and will invoke a lambda function using as input some of the attributes contained in the message. This lambda function will be responsible to actually decoding that payload into something that can be used by our downstream consumers. If we take a look at into the lambda implementation, you will see that the first thing we do is perform a base64 decoding, and then we take the base64 decoded version of the message through a series of transformation in order to eventually produce a JSON document that contains all the decoded attributes. Now that we have the decoded payload, the next step will be actually sending it down to a new topic. We are basically republishing that into a new topic, which is a quite simple action. We have a second rule that is associated to this decoded topic, and we are not really doing any transformation or filtering here. Instead, we are simply forwarding it to our detector model implemented in AWS IoT Events. AWS IoT Events is a service which is part of the AWS IoT family of services, and it's intended for doing complex event processing. It is something that you can use to basically model the different states that your model uses, and also the transition between these. In this specific case, we have three main states. We have a state where we don't really have any information. We have not received data from the sensor yet. And as you might expect, you have two additional states: when the plant is healthy and when the plant is dry. The transition between these states are basically conditioned by messages that are coming from AWS IoT Core, ultimately from the device. And as you might expect, we have a condition associated to this transition. In this case, we are comparing the observed value for our moisture with a pre-configured threshold. Right now, we assume that anything above 20% is considered a healthy status, and anything below is considered a dry status. As you might imagine, the corresponding transition in the opposite direction uses the opposite condition. In addition to this transition, each of these states can have actions associated to entering the state. We take a deeper look into these actions, we can see that we are executing or we are sending a notification using SNS. This is the mechanism that will enable you to actually send an SMS message to the user whenever a transition between healthy and dry or the opposite happens. You can see also the payload being used. If we inspect the corresponding action entering the dry state, it will be very similar. The main difference will be that here we are sending a different message. We can take a quick look at the current value for the state as well as the input variables. And as you might expect, right now we are in a dry status, right? We are not really sensing any moisture in the soil. So now I will basically plug in the device into the plant, okay? And we should be getting a signal here. We are sending data every 10 seconds, so we should get a new reading quite soon. Okay, as you can see here, our level of moisture is above the threshold, is about 20%, so our IoT events detector model should have transitioned into the healthy state. Let's take a look into that, but I know it already happens because I have received a notification on my phone. Okay, now you can see that because the level of moisture is above that threshold, we have transitioned into the healthy state. Okay, so that's basically about the uplink data flow. As I mentioned before, it's complemented with a downlink data flow. In this case, the user can use the web application to send messages down to the device. This message will be sent into a command and control topic that is also associated to an IoT Core rule that will be invoked in a Lambda. This Lambda will simply use the API coming from AWS IoT Core for LoRaWAN service in order to send message down to the device. This message will be sent by AWS IoT Core for LoRaWAN to the gateways and eventually will reach out the device. In the specific case of the device, we can send downlink message to control the frequency of the transmission. Right now we are sending data every 10 seconds, but let's take a quick look into how you can control that. Let's increase the frequency to 5 seconds and let's send it. Now we should be able to see that message in the corresponding command and control topic, and here you can see the encoded version of that command. And as I explained before, there is a rule, a third rule that is associated to that topic and will basically invoke a Lambda function that will use the API for AWS IoT Core for LoRaWAN in order to send the message down to the device. This is the statement that we just saw. Now we should validate that the frequency has been increased by basically taking a look into the messages that are now being sent, hopefully every 5 seconds. If we compare the timestamp, we can see that now the frequency has increased to 5 seconds instead of 10. So that basically concludes the demonstration. As I have been showing, you can see both the uplink and downlink message flow. So now let's go back to the presentation. To finish, I would like to refer to what some of our customers are doing already with AWS IoT Core for LoRaWAN. First, I would like to talk about ComplianceMate, which is a company in the food safety industry. ComplianceMate has built a system that allows their customers to maintain compliance to food safety regulation. ComplianceMate is using AWS IoT Core for LoRaWAN to connect temperature and humidity sensors in refrigeration units inside restaurants, and they are doing that for monitoring and reporting purpose. The second customer is Quex. Quex is a company in the property management software sector that are using LoRaWAN technologies as part of their home automation solutions. They have built that solution around a single LoRaWAN gateway that connects to AWS IoT Core for LoRaWAN, providing connectivity within the entire property in order to provide a full range of wireless devices that includes smart thermostats and door locks. Okay, so that's basically what I want to present today. My invitation is to please go and start using AWS IoT Core for LoRaWAN to build your own private networks and turn the data into business value. You can build solutions by leveraging the whole richness of the AWS ecosystem. You can find additional information in the links provided in the slide. You can access the console. You can also check some of the samples that will help you to start building solutions. And you can also definitely access the devices that has been validated in order to connect with AWS IoT Core for LoRaWAN. Thanks a lot, and I hope that you keep enjoying re:Invent.